Burn a single kilogram of coal, and you release about 10 million joules of energy. It's the chemical reaction that powered the Industrial Revolution against 100 trillion. Traditional fire relies on rearranging the outermost parts of an atom, the electrons. The energy exchanged in those chemical bonds is measured in small units called electron volts. To find that million-fold jump in power, you have to look past the electrons and go a few femtometers deeper, into a space so microscopically small it completely redefines how matter behaves. We are leaving the familiar rules of electromagnetism behind and entering the domain of the strong nuclear force. The existence of this deep atomic core wasn't obvious. Analyst Rutherford's early scattering experiments proved that atoms are almost entirely empty space, with a highly dense, positively charged center. If you expanded an atom to the size of an entire classroom, the nucleus sitting in the middle would be no larger than a pinhead. That extreme density creates an immediate physical problem. The nucleus is packed with positively charged protons. Under normal electrostatic rules, those protons should violently repel each other and tear the core apart. When Rutherford fired tiny positively charged alpha particles at a target of gold atoms, most zipped right through the empty space, but the ones that got close to the core suddenly veered off, repelled by that concentrated positive charge. The mystery of how the core actually held together was solved in 1932, when James Chadwick discovered the neutron, a particle with roughly the same mass as a proton, but carrying zero electric charge. Neutrons act as a buffer. They allow a completely different interaction, a short-range attractive force, to grab hold of the particles and overpower the electrical repulsion. But this force only works when the protons and neutrons are practically touching. When you measure a nucleus, you find something strange. An oxygen atom has 8 protons and 8 neutrons. But if you weigh an assembled oxygen nucleus, it is actually lighter than those 16 individual pieces weighed separately. Physicists call this the mass defect. A fraction of the original physical matter simply vanishes when the nucleus is put together. Albert Einstein's equivalence equation, E equals mc squared, shows us exactly where it went. Mass is a highly concentrated form of energy. When those protons and neutrons fall together and bind, that missing mass is converted directly into energy and radiated away into space. The binding energy holding the nucleus intact is literally the evaporated mass of its own components. This chart shows maintenance of the binding energy per nucleon across known elements. It acts like an energetic landscape, mapping out how tightly the core of an atom is held together. The curve rises sharply and hits a peak right around an atomic mass of 56. This is iron. At roughly 8.8 mega-electron volts per nucleon, iron represents the most stable atomic configuration in the universe. Elements on the lighter left side of the graph, like hydrogen and helium, are less tightly bound. When they are squeezed together in the center of a star, they fuse, climbing up the curve toward that stable peak. Elements on the heavy right side, like uranium, suffer from too much electrical repulsion. To reach stability, they have to drop mass, splitting apart to slide backwards up the curve toward the center. Every nuclear reaction is just the physical universe trying to shed excess mass to find a more stable resting state. When a massive nucleus breaks apart, the 2 smaller fragments that are left behind sit higher on that binding energy curve. They are more tightly bound than the original atom. Because the final pieces require less total mass to stay together, the difference is violently expelled. A single stray neutron can cause a heavy, unstable core to elongate and snap. That snap releases energy in the millions of electron volts. It is an interaction governed entirely by the short-range strong force, bypassing the weak chemical bonds of the electron shell. We capture that release of mega-electron volts as raw heat, using it to boil water and drive massive industrial turbines. Our daily experience of fire and fuel happens entirely on the outer edge of the atom, but the power that actually sustains the universe is locked deeply in its center.